11. From the balanced molecular equations, write the complete ionic and the net ionic equations for the following. And then we have letter C of the bunch. So we have CaCO3 solid plus H2SO4 aqueous will yield CaSO4 solid plus CO2 gas plus H2O liquid. Okay, so right here, right now, we have our molecular equation, okay? Molecular equations have basically three things to them. They have only compounds or things that are in elemental stages or elemental states like O2, N2, right? Or just the elements by itself. But the key thing here is that molecular equations do not have charges. The second thing that molecular equations have are the states, whether it's a solid, aqueous, gas, or liquid. And then finally, molecular equations need to be balanced. But just like every equation needs to be balanced, so that's nothing different. Now, they said that this was balanced already. Thank goodness. So we're not going to even check it. So I'm just going to rewrite what we have over here. Okay. The next thing is from a molecular equation, we could always get a complete ionic equation. Let me just finish writing this out. Perfect. So from a molecular equation, we could always go for the complete ionic equation. And what that is you're now starting to turn your molecular equation that didn't have any charges or ions into a formula that has ions in it. And remember, ions are just charged elements, right? Charged atoms. So for example, Na plus 1 would be an ion. It has a charge of a plus 1. S2 minus would be an ion, right? All of the polyatomics are called polyatomic ions because they all have a charge in that upper right-hand corner. This is sulfate, right? So how do we go from a molecular to a complete ionic? The answer lies in what states these compounds are in. So if I just group them together, it looks like I have a solid, right? I have a aqueous component. I have another solid. I have a gas. And I have a liquid. So I'll just put it in the same color. The key thing here is that, let's just put this on this side, that if your compound is aqueous, aqueous means that you will dissolve in your solution. So you will dissolve, aka you will break down. What are you going to break down to? You're going to break down into your ions. Only aqueous guys will break down into the ions. So all the other states, solid, liquid, gas, they do not dissolve. They do not break down into their ions. They will just be left all by themselves. Now, when you do break down into your ions, right, you're always going to break down into two separate components, the positive charge and the negative charge. So let's just run through this. Calcium carbonate was a solid. According to what we just said, solids do not break down into ions. So I can't really do anything with this guy, right? When I make my complete ionic equation. However, H2SO4 is aqueous. That means it's going to break down. And it's going to break down into its two separate components. And if I just put down H2SO4 up here, right, what do you think it's going to break down into? This is where your knowledge of polyatomics really come into play. Because I know that SO4, we've seen it time and time again, that SO4 is a polyatomic ion by itself. So I know the break between H2SO4 has to be between the hydrogen and the SO4. Keep in mind that when you break down compounds, you could only make one clear break between two elements. You can't make two breaks, you can't make three breaks, it's always going to be one break, Okay, so you just have to say, is it between the H and the SO4? Or is it between HS and O? Since SO4 is a polyatomic we see time and time again, we know that that's where the break is. So, if I break this, hydrogen is going one way, and the sulfate, SO4, is going the other way. Now, if I look over here, CaSO4 is a solid, so I can't do anything with that. CO2 is a gas. Gases don't break down, so I can't do anything with that. And H2O liquid, it's a liquid, so I can't do anything with that. The only thing that I could break down in this equation is the H2SO4. So, let's just write it out. The complete ionic now is going to be CaCO3 solid plus, now let's try to break this down. Well, just like, remember when so maybe I'll say like Na, right? What happens when I take Na plus 1 and mix it with O2 minus, right? How did we form that compound? We did the crisscross method, right? The 1 comes down here telling me that I only needed 1 oxygen. The 2 comes down here telling me that I needed 2 sodiums, and my compound was Na2O. However, if you're given your compound, you can crisscross back up to get your charges. The 2 told me that oxygen was a -2. And it's a negative because standard notation, the positives are always in the front and the negatives are in the back. That's how chemicals are written. There was 1 oxygen, you crisscross that up, that told me that the sodium was +1. And if we know the trends on the periodic table, this makes sense, right? Sodium's in group 1, so it's got to be a +1. And then the oxygen trend works as well. So we can do that here, of course. You can also just kind of know your polyatomic charges, which would make, everything easier. But if we just go by what we tried to do earlier, there was H2 and the polyatomic was SO4. I don't see parentheses around it, right? So I know that I only had 1 of them. And there are your 2 numbers. The 2 crisscrosses back up to tell me that I had a -2 for my sulfate, and the 1 crisscrosses to tell me that it was a +1 for my hydrogen. And does that check out? Yeah, it does, right? If you look on your polyatomics, SO4 is always a -2, and hydrogen's in group 1. It's a +1. So that checks out. So maybe I will just write that down over here, right? This was H +1 and SO4 2-. And that's exactly what you have to write now. You cannot write it as anything else. So H +1 plus SO4 2-. But now we have to say 2 more things. You have to say the states. It was aqueous, so that means both of them are aqueous. And now you just have to tell me how many I had of each. But now in a molecular compound, how many hydrogens did I have? I had 2, right? But if I put a 2 down here, that's going to change my ion. My ion has to stay H +1. So what's another way that I can say that I have 2 hydrogens? Oh, I can just add that in the front, right? I could put the 2 in the front. And that would say that I have 2, right? 2 H +1s. That's how you do it. All the numbers that are the subscripts for quantity always becomes a coefficient. However, this 4 stays a 4 in the subscript because that was the identity of sulfate. But how many sulfates do you have? You only have 1. So that you could put a 1 in front, but you don't have to. We don't put 1s, right? Okay, moving on. This is a solid, so I can't do anything with that. That stays. This is a gas. I can't do anything with that, so that stays. CO2 gas. And then H2O is a liquid. That's the end of that. And now we have our full, complete ionic equation. So write that down. Now I have to go from a complete ionic to a net ionic. Okay, so net takes into consideration all gains and all losses, right? If you have the same exact ion on the left side as you do on the right side, you will get rid of them. Those are called spectators. So that's the difference between complete ionic reaction and a net ionic. A net ionic, no spectators allowed. Because spectators don't really do much to any work, right? They don't do anything. They just watch. It's kind of like spectating at a sport match, right? If you go to any sport match and you go watch your favorite team play, let me know in the comments what sport you like. I like tennis. I love tennis. I live for tennis. Yeah, when I go to a tennis match, I'm just a spectator. I sit in the stands and I watch my favorite tennis players play. But I don't do any of the work. I just go and watch. That's what spectator ions do. They just literally chill, right? And they don't do anything. Now, I see that I have a 2H plus here, right? But do I have a 2H plus over here? No. So that's not a spectator. If I have a SO4 2 minus here, but do I have a SO4 2 minus here? No, I don't. I do have an SO4, but since it's not identical to this, I cannot cross it off. But let's just say, you had a SO4 2 minus, and then on this side you had an SO4 2 minus. Literally, it's the same exact thing. Then they will cancel, right? But we don't have that here. So do we have any spectator ions? No. So can we cancel anything out? No. So in this case, and sometimes it can happen, your net ionic equation is the same as your complete ionic equation. Yay! In this case, we didn't have to do any more work. So it would literally be the same exact thing as you wrote out because you don't have any spectators. SO4 2 minus aqueous yields CaSO4 solid. Isn't that beautiful? Okay. Sorry, I'm running into the subscribe button. If you want to click it, that's fine. But you guys have the answer up here. Okay, so, guys, what'd you think? This was fun. Let me know in the comments what you thought, if this helped you or not. And yeah, I love helping you guys out, and I want to know how you guys are doing, all right? Let me know how you're doing in your chem class, and if you're in math class, we have videos for that too. We have physics videos if you guys are in those classes. We'd love to help you guys out, okay? So I'll speak to you soon. I hope you have a great day. Take care. Bye-bye.